NASA has a mission protocol which says if a low Earth orbit mission increases the lifetime risk of the crew getting cancer by more than 3%, then they won't go ahead with it. But the upcoming Mars missions may expose the crews to levels which will be beyond that limit and to other hazards. So how dangerous is deep space travel to Mars and beyond? With Elon Musk pushing to get men onto Mars by the mid-2020s and NASA looking to do the same for the 2030s, just how much have we learned since Apollo and from the space stations? 50 years on from the beginning of the Apollo missions, and we have yet to send any man back to the moon, let alone on the much more arduous journey to our nearest viable planet Mars. Now, whilst much of this has been down to the lack of political will in the face of our own man-made problems here on Earth, it's also down to the increasing sophistication of robotic probes and landers that are much cheaper to make, launch, can go where no man could go, and can continue working for years at a time. The Voyager probes, for example, are still going 40 years after their launch. If we relied upon man discovery only, we would know a fraction of what we know now. With data from probes that we have sent around the solar system since then, we have built up a picture which is far from a vision of just whizzing through interplanetary space. That, and along with the joint NASA-Russian experiment of having men in space for a year on board the International Space Station, we now have a much better understanding of what they may experience on the 2.5-year round trip to Mars. We humans evolved on Earth, and our bodies are adapted for moving around under the effects of 1g of gravity. Take that away and problems start to arise with our physiology. We often forget what a sheltered life we all lead here on our little blue dot in the harshness of space. We're protected from 99.9% of harmful radiation, not only from the Sun, but also from other galactic sources by our atmosphere, the Earth's magnetic field, and the Van Allen belts. Yes, they may be a pain for space travel, but they do protect us from further radiation on Earth. Get beyond the shelter of these and open space is far from empty. It's teeming with not only radiation from our Sun, but also much more powerful radiation from outside our solar system in the form of galactic cosmic rays and gamma rays. Most of the hard data we have about the levels of radiation in deep space comes from the Radiation Assessment Detector instrument, which was on board the Mars rover Curiosity, part of the Mars Science Laboratory, which was launched in November 2011. The Radiation Assessment Detector was turned on for about 220 out of a 253-day journey to Mars, and showed that the radiation levels were between 100 and 1,000 times higher than that on the Earth for an unshielded occupant. But it was highly variable and depended a lot on the solar activity at the time. Experiments done on Earth with beam accelerators, computer modelling, and confirmation from the Cosmic Ray Telescope on the Lunar Reconnaissance Orbiter as it goes around the Moon have shown that plastics with high hydrogen contents are more effective than the same weight of aluminium at stopping particle radiation from both the Sun and galactic cosmic rays. And this is being incorporated into the latest spacecraft designs like the NASA Orion and the SpaceX Dragon 2. Galactic cosmic rays are protons and nuclei of atoms which have been expelled from supernovas and other violent cosmic events, and have been accelerated to near the speed of light. Because of this, they have a much greater energy level and can pass right through the spacecraft and the crew. Shielding helps, but it's a compromise between the thickness of the shield and the extra weight involved, which makes it more difficult then to get it into space from Earth. To contend with solar flares, a radiation shelter in the craft where there is extra shielding has been proposed for the SpaceX Mars mission. Liquid hydrogen or water storage tanks around the crew areas provide a good shield against particle radiation, and creating a strong magnetic shield around the crew areas are all possible, but don't protect well against electromagnetic wave radiation like gamma rays. Using the Curiosity data, it's been calculated that the radiation risk of a return journey to Mars will be about 600 millisieverts, equivalent to about 50 full-body CT scans over that period, or being on the International Space Station for 4 years straight. This is also about 30 times the yearly allowance for a radiation worker, and that doesn't include the stay on Mars itself. A dose of 1 sievert or 1000 millisieverts is associated with a lifetime increase in fatal cancers by about 5%, which is near the level of the whole mission including the stay on Mars. This would be a career limit for any of the crew, and young women are at a higher risk of cancer from radiation compared to older men, so that could affect the crew makeup. Along with the cancer risk, there is also the increased chance of developing cataracts as the radiation passes through the eye. Recent research has also suggested that the effects of galactic cosmic rays damaging brain cells at the molecular level could cause brain damage similar to the onset of dementia, which could show within the duration of the journey. Away from the radiation risks, there are also the physiological effects of microgravity on the human body. NASA astronaut Scott Kelly spent 340 days in space on the International Space Station, and even with a tough 2.5-hour exercise regime each day, he still experienced problems with circulation, eyesight, as well as loss of bone and muscle mass. Once in space, the fluids in the body no longer have gravity to pull them into the lower extremities, and are equally distributed around the body. One of the effects of this is to make the backs of the eyes swell up and alter their shape, which affects the vision. Stays on the International Space Station of a week were quickly reversed when back on Earth, but lasted for much longer after several months in microgravity. On Earth, the heart pumps blood around the body and the veins in the legs squeeze the blood back to the heart. In space, the same amount of blood is being pumped by the heart, but there is much less effort required to return it to the body. This allows the cardiovascular system in the legs to weaken over time. Again, when returning to a gravity environment, this can cause extreme dizziness and fainting due to the lack of blood being returned to the upper body and brain, which could occur when they reach Mars. Within 5 months of being in a microgravity environment, astronauts can lose up to 40% of their muscle mass and 12% of bone mass. This increases the risk of bone fractures when returning to a gravity environment, and it's like turning a 20-year-old into a 60-year-old in just a few months. Psychological issues are also a problem for people in isolated areas for long periods. Some scientists that work all year round in Antarctica suffer from a mental health disorder called winter over syndrome, which is characterised by symptoms such as depression, irritability, aggressive behaviour, insomnia and memory problems. All the sort of things you don't want to happen when trying to perform mission-critical tasks in space or on Mars. Humans travelling in open space is always going to be a risky business, and in the end, some say the risk is worth the reward of getting men to Mars. They can do much more than a robot in a short space of time, and they are much better at handling unexpected situations. But dead or dying crew is something no one wants to see beamed back to Earth, so it's in all our interests that the risks are minimised as much as possible. It will be over 50 years since the last Apollo flight by the time the earliest Mars missions come around, so even if it does take a little bit longer than expected, it won't make that much difference to make sure that we get it right. What do you think of the Mars missions and the risk of travelling in deep space? Let me know in the comments below, and don't forget to subscribe, rate and share, and also check out some of our other videos which you may find interesting. So thanks for watching, and I'll see you in the next video.